So now that we've introduced this idea of chemical potential and the fact that chemical potentials are equal when things are in equilibrium, we can use this to derive some useful relationships when we're thinking about phases, about pressure and temperature in a relationship here. So here we're going to use the idea that we know that chemical potentials of different phases are equal. So we'll call our phases alpha and beta to keep this general, right? This is not specific to solid or liquid and gas. It can work for any of them. And we know that these are equal to each other at equilibrium. Okay, so chemical potentials are a function of temperature and pressure, so we can go ahead and write out their total derivatives, right? Because they're Gibbs energies, and Gibbs energies depend on temperature and pressure. So we can say that a change in mu is equal to a change in mu for alpha, same as change in mu for beta. These are just Greek letters, alpha and beta here. Means that we can say d mu alpha dp at constant t times dp plus d mu alpha dt at constant p. So this is just using the fact that mu is a function of temperature and pressure. We're just writing out the total differential. This is times dt. This is equal to the same thing, but for d mu beta. Plus d mu beta dp, sorry, that should be dt, constant p, dt. Okay. But we just showed that mu is equal to the molar Gibbs energy. And so therefore we can use some Maxwell relationships, right? That d mu dp at constant t, well, these are not the Maxwell relationships, but some of the relationships we were looking at earlier, right, is equal to dg bar dp at constant t, which is equal to v bar. And same thing for d mu dt, right? Change in chemical potential with respect to temperature is equal to dg bar dt at constant p is equal to minus s bar. Right, these are the same relationships we were looking at earlier this chapter. So we can go ahead and make those substitutions, right? That we can say that, all right, the pressure with respect to temperature, so this partial derivative here, let me use a different color. This partial derivative here is going to be v bar of phase alpha. This partial derivative here is going to be negative s bar of phase alpha. And we have the same thing here for phase beta. And we can make the substitution here. Okay, so we have v bar alpha dp minus s bar alpha dt is equal to v bar beta dp minus s bar beta dt. All right, and we're almost to our Claperon equation. What we want to do now is express this as a slope, a change in pressure over temperature for something that's in equilibrium. And this is the slope of our coexistence curve. And this is what makes this equation useful. And now we're relating it to properties of our phases. So we can say if we solve this, right, so we'd have to rearrange it. But skipping a few steps of algebra that you can work through on your own, we can say that s bar beta minus s bar alpha divided by v bar beta minus v bar alpha, right? The pressure, temperature, that slope, the change in pressure over change in temperature of the coexistence curve is equal to the difference in the molar entropies divided by the difference in the molar volumes for those two phases. We could also just write this as, right, this is the change in the molar change in entropy for the phase transition divided by the change in molar volume for the phase transition, delta S over delta V. Now there's one more substitution we can make. So we can write this just in terms of entropies, or an alternative form is to say, well, we know that the change in molar volume at phase transition is just delta H bar at the phase transition over T at the phase transition. And this is something we talked about with the third law of thermodynamics, right? Because delta H is equal to Q at constant pressure, and there you go. That's just the definition of entropy. So we can say dP dt. Again, this is for the coexistence curve where things are in equilibrium, is equal to the change in the entropy divided by the change in the molar volume, or the alternative form is to write it in terms of the enthalpy, right? So the enthalpy, molar enthalpy of the transition divided by the temperature of the transition times the change in V bar for the transition. Let me keep my notation straight here. There we go. Okay, and this is the slope of the coexistence curve on the PT phase diagram, and this is what's known as the Claperon equation. And we can use this to predict how phase transitions change with pressure or temperature, and this can help us understand what's going on with our phase diagrams. In the next video, we'll look at an extension of this equation applied specifically to the liquid-gas equilibrium. That's called the Clausius-Clapeyron equation, where we can make some simplifying assumptions and get a more specific version of this.